Welcome to the second lecture of the module Robot Statics. In this module, I'll discuss on gravity compensation and I'll try to resolve external forces and the torques to joint forces and torques. So let us begin with gravity compensation. What is that? Gravity compensation torques are the minimum amount of joint force and torque that the joint actuators should provide even when the robot is stationary. So I want physically to make this robot floating in the air, okay, as if it is in space, as if there is no gravitational pull which is pulling the robot arms downward, okay. So applications of gravity compensations are lead through programming, in which you have seen in this video that I have shown in the application video in my first lecture. So you can see it directly here. So in this case what I was doing, I could drag the robot to any points on the programming frame. Okay, I have taken my robot to first point, second point, third point, fourth point. I can drag the robot physically. Even though the robot is quite heavy, I could not feel it because it was gravity compensated from within. Okay, all the joint actuators were providing enough torque to make this robot float in the air. Okay, so I was able to take this to different points. So once I take it to different point, I can teach it and the robot can repeat it back those taught points. That is known as lead through programming. That is one of the very common thing which is there in cobots. Okay. Controller implementation with floating robot model, they behave uniformly in all the directions. So you see a regular controller scheme that we will be discussing very much in detail in the module control, robot control. Okay, so this is the gravity compensation. So this is an external compensating torque which is continuously acted at the robot joint, so that robot becomes floating in the air and it behaves uniformly in all the direction. Thereafter you apply it with the input velocity, input position commands, force commands, everything else. Okay, so this is why it is very important, and these are the places where gravity compensation is utilized. Okay, so the prerequisite to begin with gravity compensation is the whole of the robot mass and mass center locations should be well known. So they are identified using identification experiments with respect to the links. So they are obtained through precise CAD models with the densities known of the material with which these robots are designed. Whole of the assembly is packed to the CAD environment and there you can calculate it, or it can be done after assembly also through identification experiments with the isolated link, or by measuring the joint torques after assembling the link to the robot. Okay, so there are various approaches to it. These are the few. Okay, so this is the link of a robot which is shown here. In CAD it looks like this. Okay, so static joint forces and torques due to gravity. Let us begin calculating that. So the forward kinematic transformation matrix for the ith frame with respect to the robot base, you know, it can be extracted using forward kinematics directly. You can calculate it. So T is equal to link transformation matrices. So I minus 1. So likewise you keep on moving I plus 1, I and so on till n minus 1, and it goes from 0 to 1. So like that. Okay. So finally it gives you the link transformation matrix. Okay. So using this you can calculate the rotation matrix of the link and the position of the link fixed frame. Okay, so that is OI plus 1. So for each link, if you do forward kinematic transformation till that link, so you can get all the OIs. Okay, so all the frame location you can calculate, as well as the orientation of the link. So this is the first step for that. Next is the position vector of center of gravities CI, CIX, CIY, CYZ with respect to the base frame is calculated using this. So how? So you already know the di is dix, diy, dyz is the position of the center of gravity of the ith link with respect to the link I minus 1. So you already know the vector this, because the link CAD geometry is well known. This can be extracted from the CAD. So this Ci with respect to one of the point which is on the body itself can be easily found out. So di is already known. So di has to be transformed and made with respect to the base frame, so that you can do this, because Ci is to be calculated in the base frame. So OI you have already calculated in base frame using this. Okay, from the top you see this equation. Okay, from where you have extracted all the OIs. OI is known, QI is also taken from here. Okay, multiply with DI, it gives you in the base frame. So all the vectors are in base frame now. So using this vector triangle, you can calculate Ci. So center of gravity location is now known with respect to the base frame. Okay. Now the intermediate vectors, that is di to k, that joins the origin of the ith link to the CG of the kth link. Okay, origin, let's say this is the ith link. So these are the vectors. Okay, so all these vectors can be found out using dik is equal to ck minus oi, ck minus oi. What is it? Ck, you have extracted here all the ck. Oi, you already know, you have taken it from here. Using that you can calculate all these vectors. Okay, so that is very, very important. So you can go k is equal to I plus 1, I plus 2, I plus 3, finally till n minus 1 and n. So let me just vanish for a moment again. Okay. So yes, so dik will be very, very helpful in calculating the moment at ith joint due to the center of gravity forces, which are gravitational forces which are here at all the links. So each of these would cause moment over ith joint. Okay, so that is what. So Ni will be the final moment. The total moment at ith joint would be equal to sum of all the mkg. Mk is k is equal to I to n finally. So all the links which are after the links joint I will have influence to the moment which is here. So sum of all the moments, k is equal to I to n di cross mkg. So effectively it gives me this. So total moments. So this becomes my total moment at the ith joint. Okay. So now net torque due to gravity at any joint I is the moment n projected along the zi axis, that is the joint axis. So sum of moments you have obtained. So project that along the axis of rotation, what you get is the torque at that axis. So torque at that axis will be projection of this, that is dot product with ei vector. What is ei? Is the axis vector, that you know it can be extracted from the homogeneous transformation matrix directly. The third column, first 3 rows. So if it is homogeneous transformation matrix, the first, the second, the third column, you can get the first 3 elements will be the axis vector. So if you have already done forward kinematics, A1, A2, A3 and finally till this you have to do this point. So that transformation matrix, the third column will have ei vector. Okay. So ei for the first will be, the first joint will be 0, 0, 1, that lies at the fixed base along the zi of the joint 1. Okay. The net gravity compensation torque would be array which contains T1, T2, T3, T4, T5, T6 likewise. So you compile them all together in a column, and that is the gravity compensation torque. This is what is to be applied to the robot continuously. Even to maintain this robot in its position, it has to continuously apply torque so as to be there. Let me show you a small video. So you see what I am doing. I am able to manipulate this robot, take it to different places directly without feeling the forces due to the gravity. Each of the link, is not very light as I am feeling it. Okay. So you see I am able to drag this robot anywhere. I can orient it, I can position it, I can put it to any point anywhere. Got it? So this is the beauty of having such algorithm. Now if the robot is made to float like this in space, you can understand it becomes very easy to apply the control algorithms now. And this also allows me to drag this robot and do teach repeat kind of operation. Okay. So this is the application of gravity compensation. Now coming to next. So resolving external forces and torques to the joint forces and torques. So what are we going to do here is any external force, if it is applied from here, let's say it is doing a grinding operation, polishing operation, okay. So any assembly task, so any quasi static task will also create interaction forces at the end effector. So how does that influence each of the robot joint? Okay. So that I can counter that external force using the joint torques. Okay, that is what I want to do here. So how much is the additional torque apart from the gravity compensation torque I have to apply at the joint so as to maintain that contact, or maybe you want to maintain a constant reaction force of some value, okay, against this wall or maybe any object. So this is what is my intention here. So applications are collaborative manipulation, that is robot interaction or human robot interaction, handling tasks in contact which are in continuous control like surface finishing task, grinding, polishing, buffing, deburring, okay, all these tasks, this is very important, okay. So in case of grinding, if you vary the amount of force, grinding surfaces will be different. So you have to maintain a constant reaction force against that surface. So that is what I want. Okay, robot assisted assembly, pick and place discrete static loads you have to do. I am picking up and placing it 5 kg, let's say. Tomorrow I want a 10 kg load to be handled. So that load will be different. So that can also be taken care of. Controller design, this is very important. We'll use that, we'll discuss this very much in detail when we'll be discussing controls also. Okay. So how we'll do it? Using the principle of virtual work, if you remember. So external wrench is WE, it is NX, NY, NZ, these are the moments, and FX, FY and FZ, this is the force. So club together it creates the wrench vector, okay, vector of moment and force, this is known as wrench. So external wrench here, okay. Tau is the, just now we have calculated in gravity compensation, similar to that, this is a torque vector. So this is T1, T2, T3, T4 up till T joint, let's say if it is 7 DOF robot, it is till 7. So that will be joint torques. Delta X, let us assume that is the small end effector angular and linear displacements, okay, that is delta X. So end effector displacement, and delta theta is the joint displacement. So using principle of virtual work, what you find is input work done should be equal to output work done. So we have assumed the infinitesimally small incremental displacement along the joint space and the task space. So delta X into the wrench, that is the linear and angular displacement, into the wrench moments and forces, Okay. So product of that is the work done at the end effector. Okay, and work done at the joint would be torque into joint displacement. This is the axis torque into joint angular displacement delta theta. So that is input work and output work, both are equated here. So this is what is principle of virtual work we have applied here. So as you already know, delta x is equal to Jacobian times of delta theta. Okay, delta x is equal to j delta theta. So that relates, Jacobian relates the input and output rates here. Okay, substituting that delta x here, what we get is wrench transpose into Jacobian delta theta is equal to tau transpose delta theta. If we cancel out delta theta here, what we get is wrench Jacobian is equal to torque. Wrench times of Jacobian is equal to torque. Mind it, this can be a square matrix or it may not be a square matrix also. Okay. So in that case you have to use J dagger, that is the pseudo inverse, if you want to calculate the wrench for the corresponding joint torque. Okay. So Jacobian may or may not be a square matrix also. So tau is equal to what? It is equal to J transpose of WE. So this is one of the most fundamental equation which we are going to use in control later on. So let me again show you a small demonstration here with a small video of external force. So this, you see, what I am doing is robot is continuously moving downwards, and as soon as it comes in contact, it will try to maintain a constant force against the surface. So this is the operation where I am trying to move the robot with a constant normal reaction force. This may be helpful to do any grinding work. Okay. So this is what I am doing. So this kind of calculation is very important in making my robot do any such task. Okay, even with the changing environment, I have moved the table and it is still maintaining the constant reaction force. Okay, so in this case, a moving environment is already I have done. Okay. Okay, so I hope you understood the significance why we are trying to do this and the gravity compensation. Both of these are very helpful in designing my control algorithm. Both of these are going to become the major components of the control algorithm. So we'll create the model based on this. Okay, so that's all for this lecture. In the next lecture, I'll discuss kinetostatic measures for robot design, that is velocity and force ellipsoids. That's all. Thanks a lot.